So today we are going to, I'm going to talk about something completely different than what I spoke about first two lectures. So in probability theory, we have looked a lot at moving points. So there's it traces out path, and randomly moving points trace out random paths, and we have a lot of understanding about such things. So the most basic examples are, simple random walks and Brownian motion, and then you have dependent random walks, diffusion processes. However, if you look at randomly moving objects of dimension greater than 0, like a randomly moving line or a randomly moving, evolving surface, then our knowledge is much more limited. Okay, so we'll call all of these surfaces, although a surface should be dimension 2, but let's call all of these surfaces in a generalized sense. So one of the things that we try to do in probability theory is to show that discrete processes have continuous scaling limits. And as we saw in the first two lectures, a scaling limit is, suppose you have a process on a lattice, then you look at the process in the scaled lattice epsilon times e to the d, and then look at its limiting behavior as epsilon goes to 0, so this kind of thing. And often, it's the interesting thing about scaling limits is that they have some universal properties that many different discrete processes. So discrete processes themselves can be very different. Definitions can be, very different from each other. But then the scaling limits are the same. So for example, many kinds of discrete random walks converge to Brownian motion. So that's a universal object. And another example is this Schramm-Loeffner evolution. So if you look at random walks, but which are kind of self-avoiding in some way, that is, they do not touch itself. And then there are other complicated discrete processes that converge to SLE. So SLE is another class of universal limit object scaling limits. So it's always nice to be able to find such universal objects. So one can ask about random surfaces. So just like Brownian motion and SLE are universal scaling limits for wide classes of discrete random processes, there is supposed to be a universal limit for discrete growing random surfaces, or at least a large class of discrete random surfaces. There is a universal limit, and here surface may mean any d-dimensional object for positive integer. And this limit process is described by this d+1 dimensional KPZ equation, or maybe sometimes called d-dimensional, sometimes d+1 dimensional. So 1 is for the evolution of time. So this is supposed to be a universal limit for many processes like this. However, what we know about convergence to KPZ is much more limited than what we know about convergence to Brownian motion or SLE. Okay? And the rigorous proofs of convergence exist for only a few classes of one-dimensional growing surfaces. But although it's very constrained, our knowledge, there is a large literature. There is a huge amount of work. For D2 and higher, so D equals 1 means just an evolving line. D2 and higher is, we know even much less than what we know about D equals 1. So first of all, the equation that I'm going to present in the next slide, so even the limit process is not well understood. So once we need to understand the limit process well before we can talk about convergence of discrete processes to this limit object. So there are some issues to resolve here. So what I will do in this talk is the first mathematical construction of a solution of the 2D KPZ equation that is dimension d equals 2, so the solution is obtained by a particular kind of renormalization of parameters, and it is possible, and it's conjectured actually, that there are other ways to do that. So there are various different ways of getting these limit objects. So it's you can arrive at different objects by different schemes, which is a little surprising because when you're considering convergence to random processes, usually the scaling is clear. So how you go to the limit is clear. And here there may be different ways of passing to different limits, all of which are interesting. So usually for processes for one-dimensional evolving points, only one way of scaling it gives you a non-trivial or an interesting limit. Okay, so here's the equation. So this, the KPZ equation, D plus one-dimensional KPZ equation, describes a growing random surface. Here X is d-dimensional and T is non-negative, and H is the height of the surface. Okay, so think of D as 2. So the point in R2, and ht comma x is the height of the surface at the point x at time t. Okay? And the equation says that it evolves according to this, this law, that the partial derivative of h is some parameter times the Laplacian of h plus some other parameter times the gradient squared of h plus some other parameter times standard space-time white noise. Okay? So I'll tell you what that is if you're not familiar. What is standard space-time white noise? So, the standard space-time white noise, it's a Gaussian field. Formally, it's a centered Gaussian field satisfying this covariance structure. That if you take the covariance between w.tx, w dot tx, and w dot t prime x prime is the Dirac delta t minus t prime times the Dirac delta x minus x prime. So you can think of it as an independent Gaussian random variable at each point in space-time, but the Gaussian variable has infinite variance. So in that sense. But more mathematically, W dot is a random distribution. So if you consider the space of some class of distributions, let's say tempered distributions, on R to the D, or R to the D plus 1 in this case, it's a random element of that space, which has a property that so if you take any distribution, you can integrate against smooth functions. So if you integrate against a smooth function with compact support, you get a Gaussian random variable mean zero and variance integral f squared dt dx. Okay, so that's random distribution. So that's space-time white noise, and then you get this equation. So this is like if you're familiar with stochastic differential equations, it's just like that, except in a stochastic differential equation, you typically have dbt. So that is time is one-dimensional. Here it's sort of like time itself is d plus one-dimensional. There is a w dot. That's how it's evolving. So that's the equation. It's not clear a priori whether this makes sense or not, and that's one of the big questions, whether this equation itself makes sense before talking about convergence of discrete processes to this limit. Okay. Any questions about this? Okay, so this equation was introduced by Kardar-Parisi and Zhang in 1986 and has spawned a huge literature, subsequent work. And as stated, it's not clear that this equation is mathematically meaningful. And one of the key difficulties is the appearance of this term gradient h squared. So when h is the solution of this equation, even in dimension 1, d equals 1, you don't expect the gradient of h to be a function. You expect it to be a distribution. And we don't know how to take squares of distributions. And mathematically, we don't know how to do that. So that's one of the basic difficulties of this system. And there are many other difficulties. So this is one. Okay, so let me talk a little bit about the case d equals 1. So most of the literature is, at least in math, most of the literature is about d equals 1. And a number of discrete models, as I said, have been shown to converge to this 1 plus one-dimensional KPZ equation scaling limits. So that sort of justifies its claim to universality, although it's not as large as the class of objects that we know are converging to Brownian motion or SLE, so it's much less, but still there is a number of processes that have been shown to converge. So how do you solve this equation? In d equals 1, there is a standard solution called a Cole-Hopf solution of this one-dimensional KPZ equation. It's obtained as, so remember there were these three parameters, nu, lambda, and d. So anyway, you can think of them as 1 if you want. So h is a logarithm of u, where u is a solution of the stochastic heat equation with multiplicative noise. So the stochastic heat equation is del Tu is del x2 of u plus u times space-time white noise. Okay, and okay, so this looks like another strange object, but in fact, this is we know how to solve this. So this is in the standard theory. We know how to solve this equation. This is a well-posed thing, and there is is understood. However, the way that this taking the logarithm of this equation gives you the solution of the KPZ equation, it's only in principle, because it follows by Ito's formula, and Ito's formula is not applicable here. So so it's not, it's very much inapplicable. It's very much rougher than what you need. So it's not clear that in what sense this gives a solution. It's only formally. So u is well defined. So log u is well, u is a function actually. So u is a function. U is not a distribution. So log u is well defined, and so h is well defined. And formally it's a solution of KPZ, but it's not clear in what exact sense it satisfies this. So this is what led to Martin Heyer's theory of regularity structures. So he gave a direct approach to solving the KPZ equation in D equals 1 without going through this Cole-Hopf transformation. So there is a, but it's much to discuss here. Yeah, so the issue arises because so when you want to show that this h satisfies this other equation, so you have to apply the Ito formula, and for that for applying the Ito formula you have to know that u has certain amount of smoothness, and so that is not there. I mean, for instance, second derivatives, u is a smooth object, so that is there, and also there are these other issues. So this solution is obtained using a renormalization. So you first smooth this white noise, and then you get a solution, and then you send this epsilon to 0, and then so then you can show that the limit, taking this logarithm, this makes sense only in certain kinds of mollification schemes. So if you do it in some completely arbitrary way, you do not get. So I don't know. It was not completely clear to me why a different approach would be needed. But Martin has a long discussion of that in his paper. And then there are other direct approaches. There's this thing called paracontrol distributions, and there are some other things that have come up recently. Now, in dimension 2 and higher, one can still set up the multiplicative stochastic heat equation, just as we had, just by replacing this by a Laplacian. You can do that, and these are now well understood in all dimensions. At least under certain kinds of renormalization, so I'll talk about that later. And D3 and higher, it was recently analyzed by Mukherjee, Shamov, and Zaitouni, and D equals 2 by Caravan-Hassan and Ziguras, and also by other people, and there's some older papers. So the stochastic heat equation, at least in a certain kind of renormalization of parameters, we understand it well. However, and this is still a formal solution of the KPZ equation, but again, but here it's much worse. Here, D2 and higher, u is a distribution rather than a function. So even defining this is not clear how to define this, let alone justify that it's a solution of KPZ. But 2 and higher, u is a distribution, so we don't know how to do that. Okay. Yeah. Yes. Yes, it does. It does show up. So there is a transition. So yes, I'll talk about that too. Yeah. So now the case d equals 2, so d bigger than or equal to 2 is problematic because we cannot work with the Cole-Hopf solution. D equals to itself has more problems. So the d equals 1 case has the special advantage, in the language of PDEs, it's subcritical, and in renormalization, it's called ultraviolet super renormalizable. And all the methods for solving KPs in d equals 1, including regularity structures and other methods, they depend on this feature. And what this roughly means is that there's a way to rescale space and time So the coefficient of the gradient squared can be made as small as we like while keeping the other two coefficients fixed. And the white noise is changed, but it's replaced by a new white noise. Okay, again, this it's also a standard white noise. So that's a subcritical nature of the object, and that allows some kind of perturbative expansions which can be rigorously shown to converge and so on. So this is all very helpful in d equals 1. D bigger than or equal to 3. The same can be done in a different rescaling. So this is infrared super renormalizable, and this was analyzed very recently by Mannion and Unterberger. Now, in the case d equals 2, you cannot do this. So this is the critical case, and in the language of renormalization, it's not super renormalizable. And to summarize this discussion, neither the Cole-Hopf solution nor these direct approaches are expected to work in d equals 2. So in some sense, this is the most difficult dimension. And also, it's the most interesting because surfaces are typically two-dimensional. So you want to understand two-dimensional growth. So now let me tell you how approaches to solving the KPZ equation usually begin. So they begin in the following way. So let W dot epsilon be white noise mollified by convoluting this with a special mollifier. So you take rho to be a compactly supported smooth function, and then you rescale it rho epsilon of x as epsilon to minus d rho x over epsilon. So you make it a little bump function, okay, bump function with a little support. And then what you do is you take a special convolution. So let W dot epsilon tx be integral of W dot dy rho epsilon x minus y dy. So this is a special convolution, and this can be made sense of. And then you consider the mollified equation. So you have the same equation, but you replace the white noise by the mollified white noise. And then you look at this, and it turns out that this can usually be solved in traditional sense. Okay, so although you're not mollifying in time, but that's all right because there's only one coordinate where it's not mollified, and so when you integrate along that, you get a Brownian motion. So it reduces to the dBt that you get in usual stochastic differential equations. So this can usually be solved. And the main question is what happens as epsilon goes to 0. Okay, so this is how the process starts, how you start thinking about solutions to the KPZ equation. Okay. So as I was telling Rajesh, that you can think about various other ways of smoothing the white noise, including both space and time mollification or some other scheme. And you should get the same solution in every scheme, and that's not entirely clear that happens. Okay, so the renormalization viewpoint is the following. So these parameters nu, lambda, and d need not be fixed parameters. You can let them depend on epsilon. Okay, and the main quest is now to vary them in a way so as to get a meaningful or interesting limit as epsilon goes to 0. So just because somebody gave you this equation with nu, lambda, and d doesn't mean that you have to produce something which where nu, lambda, and d are fixed. You can vary them with epsilon, and the idea. Well, additionally, for the KPZ equation, one may need to subtract off a large constant, c epsilon, depending on epsilon. And the idea of renormalization is that you vary them in a way so that the scaling limit is meaningful or interesting. Or in classical quantum field theory, it means that it yields numbers that match experiments. So this is how you should vary the parameters as epsilon tends to 0. So this is what's called in physics removing the cutoff. So there is a cutoff, and they remove the cutoff. So we'll adopt this viewpoint, and we write down this modified equation, which is the same equation, but here nu, lambda, and epsilon, d are allowed to depend on epsilon, and you subtract off a large constant c epsilon, and you want to vary them in a way so that there is some, it converges to some interesting limit as epsilon goes to 0. Okay. So note that there may be multiple ways of doing this, okay, and that's that's a little weird. You would think that there would be only one way of doing this, or up to some rescaling, there is only one way of getting. But it turns out that it is possible that in the KPZ in dimensions 2 and higher, you can have many different ways of getting limits which are not completely uninteresting. That is degenerate. That is a constant function or something like that. So when d equals 1, it turns out there is only one way to do this, and and which is that keep nu lambda and d fixed and vary this C epsilon. So this is made to blow up appropriately. Epsilon goes to 0, and the way you blow it up is so that this H epsilon, this surface, always has mean 0. So you subtract off appropriately, so the surface always has mean 0, and when you do that, you get a limit as epsilon goes to 0, limit object, and that's the solution of the one-dimensional KPZ equation, which is a well-defined, which is a function. So it's not a random distribution. And in fact, this is a Cole-Hopf solution in d equals 1. In d bigger than or equal to 3, what was done recently was that lambda epsilon was made to scale like, so this middle coefficient was made to scale like epsilon to the d minus 2 over 2. So it was sent to 0, and the C epsilon was blown up appropriately, and the other two were fixed. And they pass to a limit which is trivial in the physics sense, in the sense that it's a Gaussian scaling limit, but it's not degenerate, so it's still probabilistically or mathematically, it's still an interesting object that you get a Gaussian scaling limit. Okay? So this was done in D3 and higher. And I'll say later on there is so this was using rigorous renormalization arguments, which are very complicated, but recently there has been a simpler proof. Okay. Any questions yet? No, so the nonlinearity is relevant in the sense that this Gaussian scaling limit that you get is not the same as the one you would get if you put lambda equal to 0. Okay, so you'd get a different limit. So nonlinearity will have an effect, but yeah. Okay, so this is what we did with Alex Dunlap, who is a student at Stanford. So you consider this in 2D, on a 2D torus. Suppose we keep nu and d fixed and blow up C epsilon, and then just like the Mannion and Unterberger paper, we scale down lambda epsilon, the middle coefficient, but now here like 1 over square root log 1 over epsilon. And then if lambda is small enough, but fixed, we show that this converges in law to a limiting random distribution, so not a random function, but a random distribution along some sequence epsilon going to 0. So it's a subsequential argument. So we do not show that arbitrarily it converges, but subsequentially. And moreover, as I just said, this limit is, we prove that this is not the same as the one obtained by simply putting lambda equals 0. So it's a different limit. So the nonlinearity has a non-trivial effect on the outcome. Okay. Okay. So this is the first rigorous result about a scaling limit for 2D KPZ. However, the way we reparameterized the parameters, that is, we sent the nonlinearity lambda like 1 over square root log 1 over epsilon, is probably not the only possible renormalization that gives an interesting limit. Actually, it is conjectured that you can get even better. So there are numerical simulations, widespread, a lot of simulations suggest that it may be possible to obtain a function-valued scaling limit, not a distribution-valued, but actually a function-valued scaling limit by taking nu to be epsilon to the 2 minus z, and lambda to be epsilon to the 2 minus z minus alpha, and d to be epsilon to the 2 plus 2 alpha minus z for certain exponents alpha and z. This is known as the Family-Vicsek scaling. And then there are also scaling arguments which suggest that alpha plus z equals 2, so they are not really free of each other. And if we assume this, then we should be scaling nu like epsilon to the alpha, lambda keeping lambda fixed, and d like epsilon to the 3 alpha. Okay, and it is conjectured that with this you actually get a function-valued scaling limit. And this is not something weird. It's actually considering the KPZ equation fixed values of the parameters, but then you scale time by epsilon to the alpha, and then you multiply the solution by epsilon to the alpha. So this is some way of seeing that. So this is open. So this is completely open, and even for the value of alpha, there is, I'm not sure, but I heard that there is no consensus, but there was some prediction that it's 1/4, but then there are numerical simulations which suggest it's 0.24 something, so it's a little less than 1/4. So I'm not sure what the, but anyway, we have no idea how to prove this kind of thing. Okay. So what we show is, now I'll tell you a little bit about the proof. So this is essentially a tightness result. And we proved that the sequence is tight on appropriate space of distribution, which shows that there is a subsequential scaling limit. Okay? So this space is a kind of a Bezoff space, and this has been used in the KPZ literature before. And a criterion for tightness on the spaces was recently available, which was very useful for us. So we used that. Okay. Now, without going into all these technical details, so let me just give you an idea of how this is done. So for example, suppose you have your solution H epsilon, and let's say you integrate against a test function phi. Okay? You want to show that this family of random variables is tight. So let's just consider a much simpler problem, but which contains the essence of the argument. So the rest is just technicalities. The essence of the argument is showing that if you integrate against a test function, this is a tight family. Okay? So we have already centered everything. So this expectation is 0. So what will suffice to show that this is tight is that if you take the expectation of x epsilon squared and you take the supremum of epsilon between 0 and 1, let's say, this is finite. So the expectation squared is not blowing up as epsilon goes to 0. So that will prove tightness, and then by results from probability theory, this will show that this has a subsequential scaling limit. Okay, so any questions about this? Okay, so how do we prove this? So the first step is to write H epsilon as log U epsilon just by going through this Cole-Hopf approach. So U epsilon is a solution to the Mollified multiplicative stochastic heat equation. And then you write X epsilon like this. And then U epsilon has a representation in terms of Feynman-Katz formula. So this is also known. And due to this explicit expression, we can take the derivatives. Remember, there are these 3 parameters, nu, lambda, and d. So now lambda is, the parameter in front of the gradient squared is lambda over square root log 1 over epsilon. Okay? So this is your lambda. So this expectation depends on those parameters. So you can take derivative with respect to lambda. And suppose we can show that that this derivative is uniformly bounded for lambda in some small range and for all epsilon between 0 and 1. This will show by just Taylor expansion that this supreme is also bounded. So instead of bounding this supreme of the expected squared of x epsilon, what we aim to show is that this is uniformly bounded. Okay, so you want to show a family of functions is bounded, you bound the derivatives uniformly. And the value at 0 will be bounded, so you can use this. Okay, so that's the first step. Now, unfortunately, when you do this derivative, this yields an expectation of the intersection time of 2 random paths chosen according to some continuum polymer measure, which is Wiener measure, which is Brownian motion with a random tilt. So you have 2 Brownian motions. You can talk about the intersection times, how much time they intersect, and try to understand that. But here it's more complicated. It's not Brownian motion. It's Brownian motion tilted by some random tilt. And that we don't know how to do. So we don't know how to calculate these expectations. But when lambda equals 0, then it's just Brownian motion. And then we know how to do. Okay? So we want to bound del lambda, derivative with respect to lambda of some expectation. We know how to bound this when lambda is 0, but we don't know how to bound this when lambda is positive. So we can again take a derivative with respect to lambda. Okay? Take the second derivative. And try to bound that uniformly. But again, this yields an expectation of a polynomial of pairwise intersections of 4 random paths according to polymer measure. The complexity increases. And we can keep doing this, and it actually grows very quickly. In k steps, the complexity grows like e to the k squared. So you have intersection times of more and more random paths, and there are not only positive, there are positive and negative. There will be cancellations. So then, how do you handle this? So it seems to become more and more complicated. So to resolve this issue, what we do is the following. We first reparameterize lambda squared beta, that's just a technical thing. And then we write g beta as expectation of x epsilon squared. So we want to control g beta by controlling g prime beta, and control g prime beta by controlling g double prime beta, and so on. Okay? So this is what we want to do. Now, the problem is that these derivatives become more and more complicated, as we said. So this is a way around this problem. and it may be useful for other things also. So what we do is we set G0 equals G, and instead of bounding G prime, we find a nicer function G1 so that G prime is bounded by G1. And then to bound G1, we seek to bound G1 prime, so we find a nicer function G2 so that G1 prime is bounded by G2. And so we find a sequence of functions, G1, G2, G3, etc., so that at each k, Gk prime is bounded by Gk plus 1. And at each time, we're reducing the complexity. So whenever we're getting this upper bound, we are making it less complex than the derivative itself. So Gk plus 1 is less complex than Gk prime. And we can actually ensure that the complexity grows like e to the some constant times k instead of e to the constant times k squared. So this is what we can do. And in fact, this gk's will come as intersection, the kth power of the intersection time of two paths, this kind of thing, or at some polynomial of degree k of intersection of time of two running paths. So now we have this sequence of inequalities. Okay, so gk prime bounded by gk plus 1, and we can understand everything at 0. So gk0 can obtain by using a Brownian computation. And then just these inequalities will tell you this, that g beta is bounded by summation beta to the k over k factorial times gk of 0. So these inequalities will tell you that you have this bound. And here, the complexity grows like c to the k, whereas the kth moment of the intersection times grows like k factorial, because they are exponentially distributed. Intersection times of Brownian motions are exponentially distributed. So these grow like k factorial. So g0 is bounded by c to the k times k factorial, which the k factorial cancels with this. So if beta is small enough, this converges. Okay? So this is the idea. So this is like a perturbative expansion where the expansion has become more complicated, more and more complicated. But we only want a bound. We don't want the exact evaluation. We only want a bound because we want to apply tightness. So then we have this trick by which this can be done by making the complex things simpler. So we get a finite bound if beta is sufficiently small, and moreover, it turns out that this bound does not blow up as epsilon tends to 0. So once we have the bound, we can inspect what happens as epsilon goes to 0, and this does not blow up, and this proves the tightness. Okay. Any questions about this? Okay, so finally, the last sentence in the stated theorem says that the scaling limit is not the same as obtained by putting lambda equals 0. So in other words, the nonlinear term has a significant effect on solution. And to prove this, I'll not go into any details. We consider a kind of Fourier decomposition of the solution and show that the higher Fourier coefficient of a non-zero contribution, whereas the contribution is 0 if lambda is 0. So it's just again, some bounds, and we use some hypercontractive arguments. So there are some things to do here, but it's a Fourier theoretic argument. So there are some very recent developments since we posted our paper in September. So in December, there was a number of papers that came up. And in fact, there is this paper of Caravena-san and Ziguras, and Nikos is visiting next week, so I think he may be talking about this next week. They can show that so this lambda, I said lambda small enough, but there is a critical lambda, and they can show that the scaling limit exists for all lambda up to this critical lambda, and it's the same thing. So it's the same kind of scaling. So lambda epsilon is lambda divided by square root log epsilon. So the nonlinearity is going like 1 over square root log epsilon. So this extends our result in a very nice way. And they further show that, in fact, the solution is the solution of the stochastic heat equation with additive noise, but with a different parameter, not by putting, not the one that you get just by putting lambda equals 0, with a different nu and d. Okay, and this is known as the Edwards-Wilkinson limit. Yes. Yeah. So above lambda c, I don't know if something has been proved, like something different happens, but it's very much expected because for the stochastic heat equation, there is this well-defined criticality above which you get some kind of degeneracy. So similar thing should happen here. Now, at this criticality, so I'll talk more about this. At this criticality, you would expect a non-Gaussian limit, which would be extremely interesting. So there is another paper by Gu who posted a paper with a similar result, like this part, but he couldn't go up all the way to lambda c. They couldn't go up all the way to criticality. And there is another one by Dunlap, Gu, Rijik, and Zaitouni, which has a much shorter proof of this paper of Mannion and Unterberger. So for d bigger than or equal to 3. So this was this original one. This is a long paper, but they have a much shorter argument for this in d3 and higher. Okay. So, so here are some open questions. What happens at criticality? Okay. So that's very, that would be very interesting if one can figure out a non-Gaussian limit. So what I hear from Antti Kupiainen is that renormalization group argument suggests that instead of taking lambda equal to lambda c, you wouldn't get something interesting. What you would have to take is lambda equals lambda c plus a correction term, where the correction term would be vanishing as epsilon goes to 0, but has to be chosen carefully. Okay? It may be possible to construct a non-Gaussian scaling limit. So this would be, you know, something very nice to do, and it seems within reach now, because you have this paper of Caravena-san and Ziguras who do it all the way up to lambda c. So there is a lot of information about what's going on. Okay. So what I showed you, the argument that I showed you is more of a general argument. So I have used this before in something else. So this is sort of a general argument for showing tightness. But what they do, Caravena-san and Ziguras, is go into this specific model very deeply, and they understand exactly what is going on. Where does the square root log epsilon, scaling help, and so this understanding is sufficiently good enough to well, to at least offer a hope that this can be done. Okay, so and the paper is very well written, the Caravena et al. Paper, so you can have a look. Now, getting this Family-Vicsek scaling would of course be amazing. And this remains open, as I said, and any other scaling that gives a non-Gaussian scaling limit would be really good. And then the other thing, very important, is that show that some natural discrete process has a KPZ scaling limit in D2 and higher. So I don't think this has been done at all. And then, so we have, so as I said in this work and the subsequent works that I mentioned in the previous slide, they all deal with a certain kind of scaling limit, certain construction of KPZ. So is there some natural process which converges to that? And that would legitimize that as a truly interesting object. But even if not, is there some other scaling of parameters which gives you a limit object to which there is some? So there are various conjectures about that. Through simulations and other things. So whether that can be done. So that's another question. So there's this Edwards-Wilkinson. The original paper itself, it derives this this stochastic heat equation. So this is, by the way, this Edwards-Wilkinson limit is not the stochastic heat equation with the multiplicative noise. It's the stochastic heat equation with additive noise, and they have it as a scaling limit of some discrete process. So it's like grains of sand falling, and then they, instead of settling down, they may move a little before settling down, and so there's this growing surface, and it'll be interesting to be able to prove that something like this converges to this KPZ limit that I just mentioned. Okay, so I think I finished a little early. Okay, thank you. Yeah.
I mean, like just from simulations or whatever.
Oh, I don't know so much about the simulations in 2D and higher. So yeah, but
you expect like below it should be Gaussian. I mean, just Gaussian fluctuation.
Yeah.
It should be.
Yeah, above that there should be lambda in this scaling. Lambda big lambda c, you should see some kind of degeneracy. I don't exactly know what would happen, but some kind of degenerate behavior.
So, I mean, if I look at a stochastic differential equation, in most cases, I know I can write it as a Feynman path integral actually. So then I can apply standard methods of renormalization theory to understand what you're doing. Wouldn't that be a very powerful way of doing it rather than?
Yeah, well, you know,
I mean,
so Antti-Kupiainen, you know, he has been doing this kind of renormalization argument, you know, for these kinds of systems, and I think, well, I think the main bottleneck would be, you know, to get all the estimates that you would need to be able to, you know, prove a theorem, that is, you know, to have the complete proof. So these rigorous renormalization arguments always extends to, you know, many pages. Like, you know, so I think, yeah, I'm not an expert on that, but I think there are some bottlenecks into in making those arguments completely precise or rigorous. So that's yeah, but yeah, but yeah. So I have seen papers, you know, where this has been proposed and people have tried with that.
can you say something also about the solution of this equation? You know, I mean, some qualitative features that you can extract from this analysis. I mean, how does the solution look like in various dimensions?
So as I said, so in this paper, they proved, so they proved that in some sense the solution is not so interesting. So you know, if you take this particular scaling, lambda over square root log epsilon, this particular renormalization scaling that I propose, if you take that, you would get something that looks like just like the stochastic heat equation with additive noise with different parameters. So it just becomes a Gaussian process. You know, it's a random distribution, so it's very rough, but it's a Gaussian distribution. And so something more interesting would happen if lambda it would get non-Gaussian. But the thing is, you would always have a random distribution. You wouldn't have a random function. Okay, and that's what this Family-Vicsek scaling that I mentioned, a different way to scale the parameters, where it's conjectured that you would get a random function, and that would be, you know, a more interesting outcome if that can be proved, or that is indeed true, which is not completely clear, but that if that is indeed true, you would get a random function. But here you have a random distribution, and if lambda is small enough, then this random distribution is in fact Gaussian. So you have a Gaussian, and it would have some correlation structure which one can try to compute, but it would be a Gaussian random distribution.
So just to clarify something, I mean, you know, usually, I mean, what we mean when higher D dimensions, that there is a roughening transition. That means there is a critical value of lambda c. So for lambda bigger than lambda c, you have a rough phase, and lambda less than lambda c, you have a smooth phase. Okay. Now, what people knew for a long time is that d equal to 2 is the lower critical dimension. Okay, where basically d equal to 1 for any lambda, you have a rough phase. Okay, this is the KPZ phase. So I think from physics point of view, I think more interesting is to analyze the rough phase, because in the smooth phase we expect it roughly. I mean, it will be Gaussian phase essentially. Yeah. So I mean, is there any result for d equal to 2 in the rough side?
No. So this is all that I know of. So these results, besides our,
these are all smooth. These are all smooth spice.
These are all smooth. Yeah. Okay. Yeah. So this is all that I know, and so. So you think if lambda is bigger than lambda c, something interesting can happen?
Yes, that's what I mean. Although this is a lower critical dimension, it's not clear. But I mean, but this is because in the lower critical dimension, it's known that the lambda c depends logarithmically on the system size, which is roughly speaking, your epsilon is behaving like roughly 1 over L if you sort of put a system in a finite size C. So it's not completely clear what is really if there is a really critical point, and if there is if there is some sort of rough phase in d equal to 2.
So what would be a rough phase like if lambda is
Rough phase means that that alpha is bigger than 0. Your roughness exponent alpha, which you call alpha.
okay?
Alpha should be bigger than 0, basically. So that's the definition of rough phase. Okay. This grow like in the normal 1D KPZ scaling, basically. So what is expected is that the 2D, I mean, it's sort of this a marginal lower critical dimension. That means, basically the system is more or less rough. I think this statement is that for lambda bigger than lambda c, it should be rough, basically. I mean, that's my, I'm not sure, but this is what I sort of feel. And in fact, there's some simulation done by Team Halpin Healy, where he takes at a finite lambda. And then he finds that actually the height distribution has the same as the Bike-Rhines distribution, at least numerically. Okay, but of course he cannot prove it. So that means there is a rough phase, at least numerically, clearly. But I don't know whether it happens just above this particular lambda c or some other lambda c or something.
I think a lot of people will be leaving, so maybe on the behalf of all the participants, we should thank the organizers for a wonderful experience here. Thank you so much.